everyone. I'm Heidi Hirsh. I'm a PhD candidate at Stanford University in Northern California, and today I'm going to be presenting a piece of my dissertation research titled Diurnal and Subdiurnal Impacts of Tropical Seagrass Community Metabolism on the Seawater Carbonate System. So before we get into the data, I want to review a little of the chemistry behind ocean acidification. Many of you, oh no. Good? Okay. Do I hold it? I'll hold it. Sorry. Many of you are probably familiar with these equations, but just for review, carbon dioxide equilibrates at the ocean surface and sets off a series of equilibrium reactions that ultimately result in a high concentration of free hydrogen ions in the water column, which reduces pH, and that's our acidification. Now, calcifiers, like our coral reefs, depend on carbonate concentrations for calcification, so CO3 2-, and when we have lots of hydrogen in the water column, that reacts with the carbonate ion and takes some of that away from calcification to give us a system more in favor of dissolution. Now, many scientists have suggested that seagrass beds may be able to buffer against this ocean acidification, and the means by which this mechanism might happen is that seagrass beds can take up carbon dioxide during photosynthesis, and that leaves us with a buffered pH. And so if some of that CO2 has been taken up, this reduces the equilibrium reactions and ultimately gives us a system that may be more in favor of calcification. So we also need to account for the fact that it's not always photosynthesis. So these seagrass beds aren't always removing the carbon dioxide. At nighttime or when there's no light, they're actually going to be undergoing respiration and putting CO2 back into the system. So how much do seagrass beds actually affect the pH, or how can we actually predict this buffering capacity? Tyler Cyranak published a paper in 2017 that I think did a good job of illustrating some of the mechanisms that might affect this buffering. So to start out, in this figure we have the blue line as our baseline, and we're looking at the change in pH. So positive change would be our buffering, and a negative change would be due to acidification. So if we increase photosynthesis, P, or decrease respiration, then we're going to expect to see higher buffering during our daylight hours and a lower acidification effect. In reverse, if we decrease photosynthesis and increase respiration, then we might expect to see less buffering during the day and an increased acidification effect overnight. Now, this is also going to be modulated by residence time. And residence time is that amount of time that a parcel of water may spend in our seagrass bed or in some kind of system. And so if we have a greater residence time, that's more time that the seagrass can act on a parcel of water. So both of those impacts are going to be bigger. So a greater magnitude in photosynthesis and then a greater magnitude in respiration. And we'll see the reverse if we have low residence time, because there's less time for the community to act on the water column. Now we can also look at spatial effects. So in this, we're also again looking at the change in pH, and in the daytime, if we have a higher volume of water, so higher tide, we'd expect to see that buffering limited. So you have CO2 being removed, but not as much per unit of volume. Whereas if you have a low tide, you're going to see a higher removal of CO2 per unit of volume of water, and also a higher influx of oxygen. And then at nighttime, you'd expect to see less of a stressful environment, so less acidic with a higher volume of water at high tide, and then low tides are going to be particularly dangerous. So in summary for this intro, the diurnal cycle is extremely important, this balance of nighttime and daytime and the processes that are dominant in each. These community metabolism reactions are going to be what drive the parameters that we measure. And for acidification, we're interested in pH. And then finally, the physics of the system. So how the tides are actually limiting or resulting in a different magnitude of the effects from these different reactions. So the objective of my research is to look more into the variability on a spatial and temporal scale of a single seagrass community and see how it affects its local biogeochemistry. And this would have implications potentially for considering these communities as buffers to ocean acidification moving forward. So I conducted research in the Republic of Palau last summer, and for those of you unfamiliar, Palau is located in the southwestern Pacific, very close to where we are now. That's us. Hi, Singapore. Within Palau, I conducted research in Koror State here, so this inset corresponds to this box. So I was at the eastern entrance to Nikko Bay, and the seagrass is in this region here, so we'll look more closely in a minute. The site, Ngeseksau Reef, was chosen for its flow predominantly. So we have a single axis of current flow along our seagrass. So this is the area dominated by seagrass cover, and then all of these darker patches are coral. So we have a thriving coral community interspersed with the seagrass here, and a unidirectional single axis of flow that is that's moderated by which direction the tide is flowing. So when we have tide going up or in, we have a single flow that direction, and then if the tide's going out, single flow in the other direction. So in order to get an idea of the chemistry and how it's changing over this bed, we needed to look at what the concentrations of our different parameters are at either end. So in this case, I was particularly interested in oxygen and pH. So we deployed sea foxes at either end of a 571 meter transect. So the sea foxes are at this purple dot and this orange dot here. And sea foxes were equipped with a CTD to measure temperature and salinity, and a flow cell where it had an oxygen optode inside and a pH probe. And then finally, we had a PAR sensor as well to measure the available light. Now, we wanted to know not only what the concentrations were at each end and how they were changing, but we needed to know how that was regulated by current flow. And so to get velocity data, we deployed an ADP, or Acoustic Doppler Current Profiler, halfway down the transect. So it's this blue dot here. And then with the data from these three instruments, we were able to determine steady oxygen flux. So we did this as a function of the change in oxygen over the bed. And then we used the depth average current flow and the length of our transect, that 571 meters. So in addition to getting better temporal resolution on how chemistry might be changing in this seagrass bed, we also wanted to see what the spatial variability might look like along the surface. And to do this, we used a custom-built flow-through system aboard a small vessel, and our flow-through measured temperature and salinity with a thermosalinograph, PCO2, or the concentration of carbon dioxide, pH and oxygen, both in this sampling cup, and then we had just a consistent pump going so that we had continuous data as we moved across the seagrass bed. So jumping into some of the data, first, oh man, this is really hard to see. So the ticks on the bottom correspond to vertical bars that are supposed to be shaded, that I don't think shows through here. But the shaded parts would be nighttime. So the ticks are midnight. So here, 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 here. And in the first, in the first panel, we can see velocity and depth data. So that's our physical drivers. And the takeaway from that I want you to notice is the higher magnitude and tidal range at the beginning and end of this 17-day deployment, and then the reduction in current speed and in the maximum range at the middle. And this drives the oxygen flux that we see. So this is oxygen flux in grams of oxygen per meter squared per hour. And you can see that at the end, when we had very low daytime tides, we see very large magnitude positive flux of oxygen into the water column. And this corresponds with high oxygen saturation. I included saturation data here, it's a percentage, to show you that at those low tide periods, we actually have saturation up and beyond 300%. So it's a very super saturated environment. And then finally, I included pH data, and the purple and orange correspond to the ends of our transect again. And again, I just want you to notice the range in pH and how it corresponds to some of that physical data. So when we have our higher and lower tides, we see a greater range in daytime and nighttime pH values. Again, increased or buffered during the day and decreased at night. So another way to look at this flux is to actually calculate the mean daytime and nighttime flux rates. And so that's what's plotted here as we move across our 17-day deployment. And the takeaway message from this plot is that we see a lot of variability during the daytime in the amount of oxygen that's being put into the water column, and perhaps less at nighttime. And then again, those magnitudes are exaggerated towards the end when we had the bigger tidal cycle. And overall, interestingly enough, the net flux was actually negative for the seagrass bed. So over 17 days, if we integrate flux over day and nights, we actually get negative 30 grams of oxygen per meter squared. So looking at that surface data, now in the temperate data, we only had chemical measurements at either end of a seagrass bed, so at either end of that 571 meters. But that doesn't tell us anything about what the chemistry looks like in between. So to do that, we looked at surface measurements along the bed. And in this first panel, I have an image that's a whole bunch of drone images combined so that we have a better look at what some of the benthos looks like. And I'd love to talk to people later about how I might be able to identify the benthos. But I've overlaid that with the chemistry. So if we're moving with the direction of flow during this transect, and this was at about noon on August 12th last summer, so we're moving from the inner side of the transect to the outer toward the ocean, we see an increase in oxygen over the bed, which makes sense. We're gaining oxygen through photosynthesis. We see an increase in pH, which also makes sense. We're removing CO2 and see that drawdown in CO2, increase in pH, characteristic of buffering. And then we see a decrease in PCO2, or that concentration of CO2, over most of the bed, with the exception of the end, which I think is probably due to something other than the seagrass in that location. And so in conclusion, this seagrass bed on Ngeseksau Reef, is definitely modulating its local biogeochemistry. And we see this in the expected patterns in the spatial variability, so the evidence of high oxygen concentrations and increased pH. And we also see it in the temporal data. However, the temporal data isn't as straightforward. We don't always have positive flux during the daytime or negative flux at night. It can be highly variable and less predictable. So I want to revisit this figure from the introduction from Saranac 2017, and just to point out that this pattern in pH is not always a simple sine curve. And our data, if we take a subset of that, this is the nighttime section. Again, the shading didn't come through. We see that on some days that influx is very high and more of a maximum, and on others it's almost the same as some of the higher values we might see at night. And so finally, for Ngeseksau Reef, this seagrass bed may buffer calcifiers during the daytime. Again, I'll remind you, I didn't actually study the impact on calcification, but overnight it's contributing to a potentially more acidic environment that is something we should take into account if we're considering seagrass beds as a mitigation tool moving forward. And this is going to vary from reef to reef. I'd like to thank all of my collaborators and funding. Thank you for a student grant to get me here. And with that, I will take any questions.
Short on time. Questions?
Yeah. Yeah, so I did a simple, here, can I select here?
Maybe you repeat the question because I'm not sure.
Oh yeah, sorry. He asked if I could explain better how I calculated oxygen flux. So in this, so I measured, the instruments actually measure saturation state, so I'll just explain. Yeah, there we go. At either end of the bed, and then we calculate concentration of oxygen from that. So we took the difference in that oxygen concentration over the length of the bed, and the way this works out is the sign ends up like this. So current going into the bed is positive. So when we have a positive current into the bed and then a change in oxygen that would also be positive, we'd end up with like positive flux. Yeah, so it's the difference between either end of the bed. So the assumption is that any change in oxygen is only due to the seagrass between those two endpoints. And that's supported. We did some drifter measurements for currents. I'd love to talk to you about it later too. Anything else?